When every device in an office is plugged into a single physical switch without any logical boundaries, you have a flat network. It is the digital equivalent of one massive room where every device hears every broadcast message sent by anyone else. This structure is vulnerable to a broadcast storm. A faulty network card or accidental cable loop sends an endless stream of broadcast requests. The switches do exactly what they are programmed to do: duplicate that request and flood it out of every single port. The network links instantly saturate with duplicated traffic. The switches attempt to process the origin of every single frame, causing their CPUs to max out and their MAC address tables to overflow. Legitimate data can no longer move. A network build without logical borders will eventually choke on its own unchecked noise. We prevent this by deploying virtual local area networks, or VLANs. They logically slice a single physical network infrastructure into completely isolated safe zones. By separating hardware into distinct broadcast domains, like VLAN 10 and 20, a broadcast storm in one zone hits a wall. This is enforced by access ports acting as strict gatekeepers. They assign devices to a specific VLAN and aggressively drop mismatched traffic. At Layer 2, the hardware switching level, this isolation is absolute. Traffic from one VLAN simply cannot cross into another. The infrastructure survives the storm, but the isolation creates an operational crisis. The accounting department in one VLAN can no longer reach the application servers in another, as they are now logically invisible to each other. In a corporate environment, these isolated VLANs span across dozens of different physical switches. We need a way to move that separated traffic across a single cable without mixing the data streams. We solve this by configuring a switch port to act as a trunk. A trunk is a specialized high-capacity link engineered to carry multiple isolated VLANs across physical divides simultaneously. To maintain strict segregation on this shared wire, switchers rely on the 802.1q protocol. Before a data frame crosses the trunk, the switch alters the frame's header and inserts a 4-byte tag to permanently identify its origin VLAN. The receiving switch reads this tag, ensures the data drops into the exact corresponding VLAN, and then strips the tag away entirely. The end user's computer never even sees it. Trunking provides the secure transit highway between physical switches, but the local isolation remains intact. Devices in VLAN 10 still cannot communicate with devices in VLAN 20. To bridge the boundary between two different VLANs, we have to move up the network stack and introduce Layer 3 routing. We use an architecture known as router on a stick. A single router is connected to the switch fabric using a trunk link, allowing it to process traffic from multiple VLANs over one physical wire. When the router receives a tagged frame from VLAN 10, it de-encapsulates it. It strips away the outer Ethernet shell and the VLAN tag, exposing the core IP packet and its true destination address. The router checks its routing table to determine the correct path. It then re-encapsulates the core packet inside a brand new Layer 2 frame, attaches a VLAN 20 tag, and pushes it back down the trunk link. By combining Layer 2 trunking for strict hardware containment and Layer 3 routing for intelligent transit, the network achieves total architectural balance. Borders are strictly enforced, but authorized data flows freely. There is a critical vulnerability hiding within this trunking architecture, buried in a feature called the native VLAN. The native VLAN exists for legacy hardware, allowing untagged traffic to bypass security checks. Attackers exploit this via a double tagging attack. They craft a malicious frame with two tags. The first switch strips the outer native tag, entirely missing the hidden inner tag. The frame crosses the trunk and arrives at the second switch. That switch reads the hidden inner tag and unwittingly forwards the attacker's data directly into a secured, restricted VLAN. Automated network features and legacy backward compatibility often serve as the most dangerous backdoors in an enterprise infrastructure. Securing the trunk requires two steps. First, administrators must manually disable the dynamic trunking protocol. This prevents an attacker from automatically negotiating an access port into an unauthorized trunk connection. Second, we isolate the threat by moving the native VLAN. By default, it sits on VLAN 1. The administrator changes it to a random, unused, dead-end identifier, ensuring no user traffic ever shares that specific pathway. These configuration changes remove the attacker's ability to manipulate the tagging process, closing the vulnerability and turning a leaky system into a hardened digital fortress. Building a resilient network requires meticulous segmentation, where each boundary is defined to keep critical systems isolated and secure.